This video is to help you review for the Unit 4 test, problems 1 through 7. You may use a calculator on this portion of the test. Okay, this is a polynomial, and you're asked to find all of this information regarding the polynomial. The first thing you're asked is to find the degree. And because this is in standard form, you can just look and find the highest exponent, which is 3. The lead coefficient is the number part of the monomial that has the highest degree. And so we can see that that's -1. So the leading coefficient is -1. The main thing that you need to know here is that it is negative. The maximum number of turns is the degree less 1. So that for this is 2, and then the actual number of turns is 2 because there's a turn here as well as up here. Your turns are oftentimes your maximums and minimums. Then we're asked to find end behavior. That's what these two questions are talking about. As x approaches positive infinity, so as you go to the right on the x-axis, you can see that the values are decreasing for the function. So it's going to negative infinity. As you move to the right, to the left, in the negative x direction, negative infinity direction on the x, the values are going up. They're increasing. So it would be positive infinity. The number of X intercepts at most is the same as the degree. So at most there are 3, but in fact on our graph there are only 2. So the actual is 2. The X intercepts are -2, 0 and 2, 0. The y-intercept is 0, 8. The domain is asking us what are the possible x values for this, and they're unlimited. Negative infinity to positive infinity, as is the range. Our local maximum is this point right here, and so if you have already put this, if you haven't done so already, you should put this in your calculator in the y equals part, because this is an irrational number, and when you do that you're going to be using this. Once it's in your y equals, look, hit second, trace, and then choose maximum, and then look at your left, set your left bound and right bound by clicking the enter button, the toggle button, and then the enter. And you should get that your maximum for this point is 0.667, and then 9.481 for the y value. Your minimum is -2, 0. So that's what these 2 points are. Just look on the graph. The increasing part of this, you read a graph, the increasing and decreasing intervals from left to right. So increasing, it's increasing along this part, and you always look at the x, the portion of x. So that is increasing from -2 to 0.667, and it's decreasing in 2 places. It's decreasing here, and it's also decreasing on this other little leg of the graph. So on the leftmost part, that, again, we're reading it off of the x, so it's negative infinity to -2 union with 0.667 to positive infinity. And these intervals are often, or they are, going to be part of your maximum and minimum, because those are your turning points, moving from increasing to decreasing. Okay, to find the local maximum and local minimum of this graph, you're going to do exactly the same thing. You're going to put this in your calculator, and again, it's the second trace. Hit second and then graph or trace, and then excuse me, not graph, the trace button is beside your graph button. So second, trace, and then choose whichever one you're looking for, your maximum or your minimum, and then toggle around. So you need to choose like a left bound, hit enter, right bound, and then it forces your graph, your calculator, to look at that little portion to give you the point. So for your maximum, that's this point right here, you should get negative 0.5 and 1.563. And then for your minimum, you have two minimums, this one and this one. So you have to repeat the process of the second trace. And your minimums are negative 2.303, negative 9, and 1.302, negative 9. Okay, given one zero of the function, find the other zeros or roots. Well, I know that because this is a third degree, and I should have 3 roots. And I can use synthetic division to figure this out. So I use my root here, and then my numbers across for synthetic are the coefficients. And I need to make sure there are no values missing. And since these are in decreasing order, 3, 2, 1, none, that's good. So bring down the 9, and then I multiply negative 2 times 9 and add. Multiply negative 2 times negative 8 and add. Negative 2 times negative 1, and I get 0. So this tells me that this started out as an x cubed, and because I'm really essentially taking out an x, this becomes 9x squared minus 8x minus 1. And so now I need to see if I can factor this, and I believe I can with 9x one. Oops, I think I got my signs backwards. It should be this way. Okay, so that would be 9x squared minus 9x plus 1x, and then minus 1. So my complete factorization, including this factor, is x plus 2 times 9x plus 1 x minus 1. But it's asking me for my zeros or roots, so I have to solve this where the function is 0. So x plus 2 equals 0, 9x plus 1 equals 0, and x minus 1 equals 0. So x is negative 2, subtract 1, x is negative 1/9. So my zeros are negative 2, negative 1/9, and 1. Again, the numbers across the top are 1, -8, 4, and 48. Bring down my 1. And then my polynomial from that would be and I can factor that as x minus 6 times x plus 2. So I already know this 0, which is 4, and from these two I get that x would be 6 and x would be -2. So my zeros are 4, 6, and -2. This means that if you put this in your calculator and you graphed it, this is at these points is where the function would cross the x-axis. Okay, for number 4, what is the result of dividing? And whenever I see it in the form of x plus or minus k, I can use synthetic division. So that's what I'm going to do. It's a lot faster. However, remember that the number that goes outside is a root. And if I'm dividing by this, it means the root is -1 because x plus 1 equals 0 is the way I find my root. And across here I have 3, 7, 0, and 5. And the reason I have to put this little 0 in here is that I don't have an x term, and so the 0 has to be in there as a placeholder. So bring my 3 down, multiply to start. -1 times 3 is -3. Then add, then multiply. Okay, so this time my polynomial is 3x squared. Remember, I'm taking out an x, so this 3 started out as a 3x cubed, but I drop it down a power since I took out an x. And now this 9 is really like it's a remainder. And how do you write remainders? Just the same way you did in regular long division. Okay, this one is not in x plus or minus k form, so I'm going to have to use long division. Again, I have an x missing, so I'm going to put that 0x in for a placeholder. I'm using 0 times x because 0 times anything is 0, and so I'm not adding any value to the polynomial. I don't need to add any 0 placeholders in to what I'm dividing into because everything's accounted for. 3, 2, 1, and none. So how many, I'm paying most attention right here. So x squared times what gives me x cubed, and that would be x. And now I'm multiplying x times x cubed is, x times x squared is x cubed. X times 0x is 0x squared. X times -2 is -2x. Now, just like in normal long division, then once you multiply, you subtract. And I'm going to distribute that subtraction. So this will be subtract, subtract, and that's going to change that subtraction to plus. So these add to 0. And I bring down the -9. Now I ask 2x, or excuse me, x squared times what equals 2x squared? And that would just be a 2. 2 times x squared is 2x squared. 2 times 0x is 0x. and 2 times negative 2 is negative 4. Again, I have to subtract all of this, so I distribute that subtraction. This becomes a plus. Those add to 0. I have negative 4x here and minus 5. So there's nothing that multiplied by x squared is going to give me that negative 4x. So this is my remainder. So again, I write it with my remainder over what I was originally dividing by. So this is my final answer. For number 6, we can get a lot of information just by looking at a graph. I can see that the intersections for the x-axis are here. My y-axis is here. It has a maximum up here. I also see that the end behavior is going down and they're going in the same direction. So immediately I know that the degree of this thing is even because the end behavior is in the same direction, and I know the lead coefficient is negative because it's going down. The x-intercepts are negative 1, 0, and 2, 0. The zeros, roots, or solutions, that's all the same meaning, just different words for the same thing. And it's really referring to our x-intercepts. It's the same place, just a different way of expressing it. The zeros are negative 1 and 2. The polynomial and factored form of least degree. So I know if negative 1 and 2 are zeros, then I know those came from an x plus 1 and an x minus 2 factor. I can see here that this curves through the negative 1 root. And so I know that that is most likely a 3. That would be the smallest it would be. If it went straight through, as this one does, I could say that it's a 1. So my final factorization would be x plus 1 cubed, x minus 2. Okay, for number 7, we're doing the same kind of thing. My points of intersection are here, so those are the big points I'm going to be looking for. This time, my end behavior is in opposite directions. So I know that it's going to be an odd degree, and typically an odd degree starts in the third quadrant going down and then goes up. And that's exactly the way this one goes. So I know that my lead coefficient is positive. The x-intercepts are negative 4, 0, 1, 0, and 5, 0. I'm just reading the points of intersection on the x-axis. The zeros, roots, and solutions are just the x values from those coordinates. And I get my polynomial by kind of thinking backwards. So x plus 4 would give me a root of negative 4. X minus 1 would give me a root of 1. And x minus 5 would give me a root of 5. Now I look at what's happening at each one of those points to figure out what the multiplicity is. If it goes straight through, it is 1, and I can see it pretty much goes straight through at each one of those. Now we haven't seen an example of this yet, but if the graph had gone through and just touched, then that means there would be a multiplicity of 2 there.